One of the most extraordinary discoveries in physics in the 20th century was that light, and therefore all electromagnetic radiation, has a double nature. In some conditions it has a wave nature, and in others the particle theory would explain it better. It undergoes diffraction and also inference, as explained in Module 5. Other effects are described by the photoelectric effect in Module 10. Like given by Einstein, he said that electromagnetic energy transfers energy from quantums or photons. James Clerk Maxwell indicated in 1864, based on solid ground theory, that the generation of electrical and magnetic energy are mutually dependent on each other. A changing magnetic field will generate a changing electric field, and the opposite. Further, these fields will regenerate each other, and they will move in the space, even if the original disturbance is removed. He indicated that they will move at the speed which has already been indicated for experimental light. This speed is near to 3 times 10 to the power 8 meters per second. In the diagram you see an electric field E, which oscillates and generates a magnetic field B that oscillates on an angle perpendicular to itself. The source of electrical fields accelerates loads. Each time a load accelerates, generates electromagnetic waves. Electrical currents that oscillate at high frequencies contain loads that oscillate to and fro. These accelerating loads give indication to electromagnetic radiation. Heinrich Hertz used high-frequency sparks to generate radio waves for the first time. The idea was first used by Marconi, who thought out a wireless telegraph. Michelson and Morley proved that an ether is not needed as a medium of transmission for electromagnetic waves as a medium of transmission. This proved that there existed a broad spectrum of electromagnetic waves, and in time the full magnetical spectrum was discovered. Later experiments showed that electromagnetic waves are polarized, which means that it's transverse waves. The figure shows the electromagnetic spectrum. There is no clear division between the different types of electromagnetic radiations. What you see in the figure vaguely explains what happens if a conversion takes place. The small part of the light spectrum we can actually see is a very small part of the millions of outlying frequencies there really are. Max Planck used ideas of a perfect emitter to derive that the energy of a photon is directly equivalent to its frequency. Blue-green light in the hydrogen spectrum has a frequency of 6 times 10 to the power 14 Hertz. What is the wavelength of light with this color, and what is the energy of one photon of this light? If you change the formula to work out lambda, you would see that you get 500 nanometers. To work out energy, we use the normal HF formula, and at the end you get 3,9 times 10 to the power minus 19 joule. The most dangerous and penetrating forms of electromagnetic radiation is gamma rays. A few centimeters of lead is needed to stop just a moderate part of gamma rays. These waves, photons, carry the most energy. Gamma rays of potent nuclear reactors are normally secluded with multiple meter thick walls made of lead and cement. It is dangerous for living tissue because it can create cancer or destroy living tissue. The same applies to X-rays, but to a lesser extent. Nurses working with X-rays take special precautions to not be subjected to radiation too much. They therefore leave the room and stand behind lead plating while the patient is scanned. Ultraviolet rays is next on the list of penetration. They only go through the surface of the skin, but they can be dangerous due to too much exposure can cause skin cancer. Ultraviolet light doesn't go through glass. That's why ultraviolet lights only use quartz glass.